Hello and welcome to this webinar 5 in a series of 7 webinars on the topics around stage construction analysis. So the webinar series breaks down as follows. There are 2 introductory webinars, the first of which I regard as pretty essential viewing in order to look at any of the rest. Then 4 webinars where we get into details on different aspects of stage construction analysis. And then a final summary webinar where I'll try and pick out the key points from each of the preceding 6 webinars. So this one, we're looking into deflection reporting. So basically going to break this down into 3 parts. Just first of all, why is this a topic? What are the concerns? And then I'll explain how the deflection reporting comes about with 2 examples. The first looking at gravity load only, and then the second where I introduce sway effects. And as I say, this is a topic which we anticipate some level of concern or confusion in this regard. So within the help system, there is an example which you can work through all of what I'm about to tell you in a different format in the help system. But basically, the problem is that in any sort of analysis, when you start to see results that you don't expect, what I'm always telling people to do is have you looked at the deflections? And if the deflections are wrong, that's the first thing to look into. Why are the deflections wrong? And sometimes that really exposes a very fundamental problem. Someone's worrying about shear forces not being what they expected, but actually something's deflecting 20 meters rather than 20 millimeters. So look at the deflections as soon as you're getting concerned about things. And for stage construction analysis, the same remains true, but there can be some little quirks that you have to expect. So in anticipation of that, we included this extra section in the help system. And really what I'm going to do here is present all of that same information. To do that, I'm going to start just by talking you through a video introducing what the concerns are. I'll use this structure to illustrate the sort of concerns that you might start to develop when you start looking at the deflections from stage construction analysis. It's actually not all that realistic a structure. It's 10 identical floor levels at 5 meter centers, so it's actually a 50 meter tall structure, and it's quite slender, and it's very highly susceptible to second order effects. So when I apply gravity load only, I've got a bunch of combinations set up here, but I just look straight away at the results for a combination where the only loading that is applied is gravity loading. You can see that it sways. Now that's an effect that you would expect any time that you have a non-symmetrical structure with vertical loading applied. There will be some tendency to sway. So that's what it's swaying when it's from a first order linear analysis. 42.6 millimeters in the X direction. I'm looking specifically at X direction deflections at the moment. So for that, if I go and look at the load combination, in that combination I've included self-weight, dead load, services imposed. The dead loads is a finishes allowance that's set to 0.75 kilonewtons a square meter on every floor. Services, again an allowance of 0.75, and the imposed load is set to 2.5 kilonewtons a square meter. I've also set up here the stage construction combination, the construction stage loading combination, and in that I've included self-weight and the slab self-weight in recent and older stages, and then in the older stages I put in all of that dead load finishes allowance and 50% of the services allowance, and then I've used the construction loading allowance to apply loads of 0.1 to a new stage, and then 1 kilonewton meter squared to the older stages. So there's a reasonably significant proportion of the total load is getting applied during construction here. If I cancel out of that and then look at the results from the stage construction analysis, you can see that for exactly the same combination, instead of 42.6 millimeters deflection, it's displacing 17.6. So this is the design stage where the load is elevated to exactly the same level. So it's quite a big drop in deflection there. Just one thing I can do here to just show how the loads are totaling up. In the combination, you can tell from this that the total load is just over 40,000 kilonewtons, and you can see from this that there is no load applied in X and Y. It's all applied in the Z direction. So that's at the ultimate limit state, and I can also look at any of the stages and see what the total loading was at that stage. So at the end of the construction stages, it was just under 25,000. So that's 60% of the load was developed in the construction stages in this idealization, and it goes up by another 40% when the loads are taken to full ultimate limit state values. So big drop. What you might first think, is that this is going to be something to do with the analysis model properties. If I go to settings, I can review my settings for building analysis. These are all the adjustment factors that I've set up, and I have actually taken the time here to set them up to be absolutely identical in the building analysis and the persistent loading strength, which is the one that applies to this ultimate limit state situation here. So I've got exactly the same factors, so it's got nothing to do with the factors why this is different. So that's it. You're looking at this big difference, thinking, why is that? Why is that? And then you start looking in more closely, and you might start to see little things like this sort of little step. It's a bit difficult to see in a 3D view. I'll swap over to a frame view on the frame there with this wall here. Just looking at this frame view, and if I zoom in, what's this little step here between the top of this column and going on to the start of that column? Why does it step over there? That seems a little potentially confusing. And then also just looking at my results, where I can see as I go from this floor, deflection seems to go back and then up and then back again, and you can start to see that happening floor by floor all the way up. So basically it's the same sort of step, but it happening stretched over a distance there. So those are the two things where you might start to look at globally at the deflections, get a bit worried, then start to look at things more locally, and then start and think, well, I don't really understand what's going on there. So the purpose of this next section of the presentation is to explain why these things do make sense, and once you understand the background to it, hopefully you can move on and not worry about it. Okay, in the video I've introduced what the concerns might be, basically two concerns, looking particularly more at sway deflections, that the reported total sway deflections might be lower than you expect and seem low when you compared with the results from a traditional first order linear analysis. And then also you can see these strange looking steps in the deflection display. So I'm going to start explaining all of that for the purpose of utilizing these two simple examples. We'll start again with what's obviously becoming my favorite sort of example, little three-story structure, the transfer beam, a single load on each level, and the load is getting applied during the construction stages. I've also set the stage durations to 0 so that I'm eliminating creep effects. So at the end of stage 1, this beam with that 100 kilonewton load on it is deflecting 5.75 millimeters. I then build stage 2 and load it. When I do that, the beam in stage 2 deflects, but the load is getting shared with the beam in the level below. So it also deflects, and its deflection goes up to 8.16, and so on when stage 3 gets built. So just looking at that a little bit more in detail, stages 1 and 2, this deflected shape tends to be perceived as quite reasonable and almost in a way understandable. But actually note that that column is in compression. Whereas if you just look at the deflections at each end of it, it's deflecting down by more at the bottom than at the top. So if you look at the deflection diagram, you're thinking that should be tension. could start to justify that in their own minds by thinking, well, it's a concrete structure. When this deflects down, when I build the next level above, I actually build something that's longer. But it doesn't really actually quite make sense when you start thinking about the deflections that are getting reported in isolation. But that does lead me into talking about the kind of two main construction scenarios. So one is that in situ construction scenario where you imagine that the column being built from level 1 to 2 would just be cast an extra 5.75 millimeters longer, so that at the point of construction, level 2 is totally level. And then scenario 2 is that it's some form of prefabricated construction. So members have been sized, taking no account of this deflection of the first floor beam before the introduction of the second floor. So when you introduce that column and then connect things to it, there will just be a built-in slope on the second floor. And it's actually quite a subtle point, but in terms of the analysis, we really don't care which of those scenarios applies. All that we know at the end of the analysis is that wherever it started at the end of stage 2, the top of that column has moved down by 2.44 millimeters. So if you built it longer, it will have still moved down 2.44 millimeters. So coming back to this view, the top of the column is deflecting 2.44 millimeters since it was introduced. And the bottom of the column is measuring the difference between these values. So it's 8.16 minus 5.75 is 2.41 millimeters since it was introduced. And so actually, over its length, since it was introduced, it has shortened, and hence this compression is logical. But the view is explicable and seems, from a gravity load point of view, is quite naturally accepted. People like that sort of view. So now I'm going to go on and look at the same sort of thing, but start looking at the sway effects. And again, starting with that same model. And in this case, I'm building it in 3 stages, but the only load that ever exists is this load, which is introduced in stage 1. So in stage 1, this is deflecting over in the x direction. And then I build stage 2, but no more loads applied. So from the point at which it's introduced, it never moves. And then stage 3, same is true again. Now when you start to zoom in on this again, you've got this, it's moved over. We've got the level above, which isn't moving. So you've got column coming down. And wherever it was actually introduced, the bottom of that column is not moving in stage 2. So what we just do is draw a joining line there. And this is the reasoning behind why you can see these small steps. And so this doesn't look as this is not as comfortable to accept as the gravity loading case, but actually the principles used are the same in both situations. And the key thing to take away from when you're looking at deflection diagrams is that deflection shown represents the total deflection since that node or member was first introduced. Taking on that example a little bit further, just putting a load at every level, again you see level 1's moved over, you add level 2 and add the load at level 2, level 1 moves a bit further, so that level 2 moves over, and so on and so on. But each time you're seeing this small step. And when we just compare the results now for stage construction analysis on the right with a linear elastic analysis on the left, you can see that this model's swaying over 1.36 millimeters at the top. And in this view, you're seeing the load, the sway diagram with the step back. So the top of the structure is only moving over 0.66 millimeters after the point at which it was introduced. When you think about it, this is really quite logical. If I have built this bottom level and loaded it, then before I ever built anything above, why would the load that I apply at first floor level be doing anything at the top? So In a first order linear analysis, you don't have that history, and that load which was applied before this structure was ever introduced is introducing deflection on that structure up there. So just some more closing notes about what actually moving on to the topic of imperfections. When we start discussing this sort of thing, people can start to think again, well, actually, wouldn't it make sense to actually build the structure offset each time? Wouldn't that be more correct, if you like? Well, we don't do that, and a couple of few reasons really. But first of all, it's not simple, because would you build it offset and vertical? Would you build it offset and try and connect it back as if you were constructing out the tolerance? There'd be options there to consider. It wouldn't be simple. And we're actually really talking about some quite secondary effects. So I think it's not worth putting effort into solving that sort of problem. And then finally, these effects of, if you as you build something and it sways, and then you'll be building out the natural sway of the structure as you build it sequentially upwards. These are effectively imperfections, and the design codes already require you to include for imperfections in some way. So in the Euro codes, that's equivalent horizontal forces to allow for imperfection. In other codes, it sort of gets buried within minimum lateral loading allowances. And this sway deflection that you see in the analysis part would only be a small part of a full imperfection allowance. So you still need to introduce the imperfection allowance, which we do, and we'll do that whether it's stage construction analysis or not. If you were to build it in again here, you would end up double counting an aspect of imperfections and potentially making the design less efficient than it needs to be. So in summary, in terms of construction, there are varying real-world scenarios: in situ construction and prefabricated construction. We don't really care which of those two things it is for the purposes of a stage construction analysis. In terms of the global structure analysis, the small impacts of either of them can be considered quite ignorable. So we don't create deformed analysis models based on the results of previous stages, and the construction imperfection is already catered for in other ways. As a general reminder, when you're looking at these deflection diagrams, the deflection shown represents the total deflection since that node or member was first introduced. And that brings me to the end of webinar 5.